Okay, we are doing practice exam number 4 today, chapters 8 through 9, 16 questions, and this is the beginning of hypothesis testing. So most hypothesis tests have some kind of claim in the problem that you're trying to prove or disprove. And here it says the claim is the mean weight of beauty pageant winners is 106 pounds. A study of 24 randomly selected beauty pageants resulted in a mean winner weight of 111 pounds. So that's where these tests come about, is that there's always some kind of debate going on. Some claim is that they're 106 pounds, but then some other random study shows that it's slightly different than claimed. So who's right, who's wrong is kind of the deal here. This process will let us know who's more likely to be correct. And it says the mean weight. So the first thing you want to do on your claim is figure out what parameter they're talking about. Is it sigma, population standard deviation? Is it mu, population mean? Or is it p, population proportion? This one's about a mean, so knowing that the symbol mu stands for mean lets you select that one. The claim can have basically any kind of equation or inequality. It can be a less than, a not equal to, equal, greater than or equal to, less than or equal to. Just about anybody can claim anything they want. This one is that the mean is 106 pounds. So is equals, and it's 106 is the claim, even though there's 111 in the sample. The claim is what was in that sentence, not in the other sentence. So once you get your claim set, the claim then becomes one of these two hypotheses that are known as the null and alternative hypotheses. And it can literally be either one of the two. It all depends whether the claim has some kind of equals in it or not. So if it's equal to alone, if it's greater than or equal to, or if it's less than or equal to, then it goes in the null hypothesis. The null has to have some kind of value of equality in it. If it's that somebody is more than something or less than something or not equal to something, the claim can be more than or less than or not equal to. And since those don't have an equal to in them, they would go on the alternative. So I always start, where's my claim going? This one has an equal, so it's definitely the null. So you just repeat what you have there. Mu equals 106. Once you've placed the claim in the first or the second slot, then you technically do the exact opposite of that in the other one. The opposite of equal to is not equal to, so our alternative becomes mu is not equal to 106 pounds. These two should always have the same parameter here, mu, and the two numbers should be the same whenever there's one sample. You would never have mu is equal to 106 and mu is not equal to 111. Or it would never be mu is equal to 106 and x bar is not equal to 106. So these two are always the same, the two mu's, and the two numbers are always the same. And what we're trying to do is set up a scenario where at least one of these two hypotheses is true and one of them is definitely false. Either all the weights really are 106 pounds or they're not 106 pounds. There's no way they can both be true. There's no way neither can be true. One is definitely true and one is definitely false. So we're always trying to set up a situation where somebody's definitely right and somebody's definitely wrong. Here's another example of this, but now it's high school teachers have incomes with a standard deviation, not a mean. The last one was mean. Now the claim is about a standard deviation that's less than, not is like the last problem, but this one says less than 22,250. So now the claim is about the standard deviation sigma being less than 22,250. So then I see the claim has a less than in it only. There's no less than or equal to, which it could have, but this one does not have less than or equal to. It's just less than. Because the claim does not have any kind of equal in it, it has to go in the alternative hypothesis. And then you just repeat it exactly what you have. Sigma is less than 22,250. So you always fill the claim in first into one of the two slots, completely dependent on whether the claim has an equal to in it or not. Once you've set that up, then the exact opposite of that goes in the other one. We want to get the exact opposite so that one of them is definitely true and one of them is definitely false. The exact opposite would be that sigma is greater than or equal to 22,250. Now, some textbooks will actually do that and write greater than or equal to right here, just so you can see these are totally opposite of each other. I actually prefer that method too. Other textbooks just put equal to in the null no matter what. And that's what this one does. So it's a little bit harder sometimes to say what the alternative is if you just automatically put an equal to in the null every time. But in here you basically can. On every problem, if you just want to put equal to in the null every time, you're going to get it right. But if you put equal to here every time, then you might think that this one's always not equal to. And that's not always true. The alternative can be less than alone or greater than alone. So to me it's easier. Fill in whatever you have in its appropriate place and then do the exact opposite of it in the other place. And saying greater than or equal to is technically the same as just saying equal to here. Because all we really care to do is prove this claim wrong. They said it was less than, so I don't care if it's greater than or if it's equal to 22.5. Both of those scenarios are the opposite of what they claimed, and they both shows that this person's wrong. So if I'm just out to prove this person wrong, I don't care whether it's equal to 22,000 or greater than or equal to. Either way, both of those are opposite of what this person's saying. So one thing just know is the null is always equal to, but the alternative might not be not equal to. And then there's one last one, just like the first two. At least 44% of internet users pay bills online. 44%. This is about a percent, so this is P, population proportion. At least means greater than or equal to. People get at least and at most mixed up. I always remember it by, you have to be at least 16 to drive a car. Everybody knows you have to be at least 16 to drive a car. And we have 16 and ups driving. We don't have less than 16-year-olds driving. So the claim is literally that the proportion is greater than or equal to 44%. Now 44%, we always work with decimals. We never work with percents in statistics. So you actually have to put 0.44, which is the equivalent of 44%. If you move the decimal twice to make it a decimal. If you try to put 44 there, it'll say it's wrong. So notice the claim can have a greater than or equal to in it. So because it has an equal to, it needs to go in the null hypothesis. And when I do these, or if I was given a free response test in an in-person class, I would actually write P is greater than or equal to 0.44 right here in the null hypothesis. But this book won't give me the choice to put greater than or equal to. They just automatically put equal to in the null every time. Because they don't really care if it's over 44, they just want it to be 44. But think of this as being a greater than or equal to. What's the opposite of greater than or equal to? The opposite of the claim is less than. So that's important, that it has to be a less than here. If you put not equal to here, just because it's the opposite of equal to, you'll get this wrong. P needs to be less than 0.44. Even when this is equal to, only because they're ignoring the greater than part of it. Technically there's a greater than or equal to in the null, they're just not writing the greater than part. Okay, so now we switch to what happens in a hypothesis test. There's actually multiple steps you do, and what we just did was just one of multiple steps that are done in a problem. Another step involves doing some calculations and taking your answers and making a conclusion from them. So they're kind of at the end of a hypothesis test where somebody claimed the proportion of male golfers is more than 0.7. So that claim would be the alternative hypothesis. We would need the alternative hypothesis to be more than 0.7 because that does not have an equal to in it. So the alternative hypothesis would be P is greater than 0.7. And I would put P is less than or equal to 0.7 in the null, or you can do this the way this textbook does it and just put P equals 0.7. These would be the two hypotheses that you can see that. I don't know if you can see that well enough or not, but the null would be either P equals 0.7, or think of it as less than or equal to. That's really the same thing here. But the alternative is P is greater than 0.7 because they said it's more than 0.7. So then the calculations are done and we get something called a p-value, and it comes out to 0.173. So what you do is you compare your p-value to this significance level given on the problem, alpha. Alpha is 0.05. And since 0.173 is greater than 0.05, this is how you want to do every conclusion. You want to compare the p-value compared to alpha. Alpha is given to you in every problem. The p-value, usually you calculate it, but here it's given to us. Set 0.173 is bigger than 0.05. Whenever your p-value is greater than alpha, you fail to reject the null hypothesis. When it's less than, that's when you can reject. And that goes back to all the way back to chapter 2 actually, where they asked you about is a probability unusual or not. And the most common unusual probability is this 5%, 0.05, although that can change slightly here in chapter 8. But the most common one is 5%. So you need to be able to get a p-value less than this 5% to have an unusual one, and then when it is unusual, then we can reject the null. Because the null is assumed to be true, just like you're innocent until proven guilty in court. It takes special evidence to show you're guilty in court, and just like that, it takes an unusual probability for us to reject the null. Otherwise, we just assume it's true. We did not get an unusual probability. 17% is not less than 5%. It's not unusual. So we don't accept the null. The only two possible conclusions you can ever make are reject the null or fail to reject the null. It's kind of like guilty or not guilty in court. They never say innocent. So we fail to reject the null because the p-value was greater than alpha. And that happens every time. Anytime a p-value is greater than alpha, you fail to reject the null hypothesis no matter what type of test you're doing. If you have a p-value that's less than alpha, you would reject the null hypothesis. So really, part B and part D are the only two possible answers you would ever put on any question. A and C are just putting the opposite of what could be possible, but they're never even possible. It's always reject the null because the p-value is less than alpha, or it's fail to reject the null because the p-value is not less than alpha. It's greater than alpha. So here's another thing that goes hand in hand. They always like to finish the conclusion with what does this mean in English more than just this general statistical terms. And if you reject the null hypothesis, then you do have sufficient evidence to either support or reject a claim, depending where it is. If you fail to reject a null, then there is not sufficient evidence. And that's a little easy to remember because fail means you did not do something. So if you fail to reject, there's not sufficient evidence. That's true every time. If you reject, then there is sufficient evidence. So I can definitely eliminate A and C because I failed to reject the null. So the difference between B and D is it says there's not sufficient evidence to reject the claim or there's not sufficient evidence to support the claim. So that goes back again to where the claim was. In this problem, the claim was that the proportion is more than 0.7. So the claim is actually in the alternative hypothesis. We're always trying to reject the null. So if the claim's in the null, we're trying to reject it. If the claim happens to be in the alternate, then we're trying to support it. So that's another, there's kind of three things that are always true. If the p-value is less than alpha, you always reject the null. If the p-value is greater than alpha, you always fail to reject the null. If you reject the null, there is sufficient evidence. If you fail to reject the null, there's not sufficient evidence. And then if the claim's in the null, whether you reject it or not, you're trying to reject it. And you either say there is enough evidence to reject it or there's not enough evidence to reject it. If the claim's in the alternate, you're trying to support it, and either there is enough evidence to support it or there's not enough evidence to support it. So there's not sufficient evidence to support the claim because there's not sufficient evidence because I failed to reject, to support the claim because the claim's in the alternate. If the claim had been in the null, I would have picked B for this answer. Okay, original claim. Women have heights with a mean equal to 152.6. So this time the null hypothesis is that mu equals 152.6. That's the claim. So the alternative would be not equal to. So you always want to do your null and alternative first so you can figure out where the claim's going to go. The claim is in the null hypothesis, mu equals 152.6. Since there's no direction to it, the opposite of that would be mu is not equal to 152.6. But the claim's in the null hypothesis, so this time I'm trying to reject it. Okay, this time again we have a p-value that's 0.184. That's way bigger than the significance level, which they changed to 0.01 this time. But the p-value is greater than alpha again. Oops, 0.01. The p-value 0.1874 is greater than the significance level they gave me, 0.01. So again, I failed to reject the null hypothesis. Failed to reject the null because the p-value is greater than alpha again, just like the last question. Anytime you fail to reject a null, there is not sufficient evidence. The previous question I said there's not sufficient evidence to support the claim because the claim was in the alternative. Now I'm going to say there's not sufficient evidence to warrant rejection of the claim because this time the claim was in the null, and whenever it's in the null we're trying to reject it. So there's the three parts of these every time. Are you rejecting the null or not rejecting the null? Is there sufficient evidence or is there not sufficient evidence? And are you trying to reject the claim or support the claim? All three of those, they work the same on every single test too, luckily. Let me just check one thing back on number 5. If I hit similar question, I guess not, that's not what I'm thinking of. Okay. I was thinking maybe we could get one where it's the opposite answer, but no, I guess not. Okay. Okay, another problem with these hypothesis tests is nothing's ever absolute. We never know if we're right or not. It's very much like in court where they decide somebody's guilty or not guilty. But unfortunately, some guilty people go free and some innocent people are punished. So there's these two types of errors called type 1 error and type 2 error. And they kind of correspond to these two scenarios. What if I reject the null when I shouldn't? Or what if I fail to reject the null when I should? So there's this textbook has a nice way to remember this. And I'll write it down here. There's a little phrase you can say to yourself that helps you remember these two types of error. And it's called routine for fun. Take the phrase routine for fun. And if you write it out, capitalize all the consonants and keep the vowels lowercase. So that way R is a capital letter, but O and U are little letters. T is a capital letter, and so on. Routine for fun. Every consonant's been capitalized, every vowel's still little. That way you can remember these two types of error. Type 1 error comes from just the routine part. The three capital letters are R, T, and N. So that stands for reject a true null hypothesis. Type 1 error comes from just the word routine. If you reject a true null hypothesis, you're making a type 1 error. So if the null is true, even if we're always out to try to reject the null, we're kind of the devil's advocate in most of these problems. we're trying to reject the null. But if it's true, we don't want to reject it. It's the same way in court. If a person's truly not guilty, we shouldn't just vote guilty no matter what just because we want to prove them guilty. If they're truly not guilty, we need to admit that and let them go. So if the null is actually true, we don't want to reject it, but we sometimes accidentally do that. So a type 1 error is always rejecting the null hypothesis when it's actually true. So this would be C, reject the claim that the proportion is 0.24 when it actually is 0.24. If it's actually true, you don't want to reject it. So if you do reject it when it's true, you're making a type 1 error. You're the one that's wrong, not what the actual claim is. The type 2 error is exactly the opposite, and it comes from the for fun part. And again, if you capitalize all the consonants, you can see it easier. And again, it always comes down to our two possible conclusions. The only two conclusions we ever make are reject the null or fail to reject the null. That's all we can do. So in a type 2 error, from the for fun part, this is when you fail to reject a false null hypothesis. So sometimes the null is actually false, and we would hope to reject it to show that it's false. And when we reject it, we go with the alternate hypothesis. But sometimes we fail to reject the null, which in essence, even though we don't say we accept it, if you fail to reject the null, in essence, it's going to stand as a reality. So failing to reject the null when it's false is a bad thing. Then you're letting a guilty person go free, basically. So you don't want to punish innocent people like in part A, and you don't want to let guilty people go free in part B here. So type 2 error is when I think of routine for fun. Routine, rejecting a null when it's true is type 1. Fail to reject a false null hypothesis. So this is fail to reject the claim of 0.24 when it actually is different from 0.24. If it really is different from 0.24, and the claim is that it is 0.24, we want to reject that, and we failed to do it. So we made a mistake here by failing to reject it. So if you remember routine for fun, that can help you answer those. A blank is a procedure for testing a claim about a property of a population. This is what this chapter is about. It's called a hypothesis test. A hypothesis test is a procedure you follow, and we've kind of only seen a few of the steps here. We're going to get to problems later where we do all the steps, but it's a step-by-step procedure for testing some claim about a population. And it may be true or false, but we're going to go through the whole procedure to figure that out. And then the null hypothesis is a statement that the value of a population parameter is equal to some claim value. So remember how the equal to, the null always has to have an equal to in it in some fashion or another. And this book even does that it's always equal to. But technically you could think of it as greater than or equal to, or less than or equal to could also be considered null hypotheses. Okay, in the calculation part of these procedures, these hypothesis tests, we usually get two calculations. We get what's called the test statistic and a p-value. The test statistic is the answer to this one. The test statistic is a value used in making a decision about the null hypothesis and is found by converting a sample statistic to a score, like a z-score or a t-score. That's really what a test statistic is a z-score or a t-score. And then the key thing for all of these hypothesis tests is that there's an assumption that the null hypothesis is true. Just like there's an assumption that somebody's innocent until proven guilty. So we assume the null to be true. If nothing unusual comes up when we calculate this test statistic, and the p-value is what's the probability that it would happen, if we don't get an unusual test statistic, we don't get an unusual probability, then we can't say anything against this assumption that the null is true. So in essence, it stands as true. It isn't that we're proving it true. You don't prove somebody's innocent. That's impossible. So you just assume that they're true unless you can prove otherwise. If you're able to get an unusual test statistic where the probability of it's very, very small and unusual, then you have evidence that there's something wrong with this assumption that you made that the null is true. So that's what we're always doing. We're looking for some unusual probability that's letting me know that it must be this assumption of a true null that's leading me to get this unusual answer. Okay, which of the following is not a criterion for making a decision about a hypothesis test? If the p-value is less than 0.05, the decision is to reject the null. Otherwise, we fail to reject the null. That's actually true some of the time. But what makes this one false is that it doesn't have to be 0.05. It could be 0.05, and that's actually the most common one. But we actually saw another one where it would change to 0.01. It usually will change somewhere between 1% and 10%. And the reason it changes is those two types of error. The p-value is compared to the level of significance, which is really the probability of making a type 1 error. So we can't control what happens with a type 2 error. We control the type 1 error. And if you think the type 1 is the worst of the two, is it worse to put an innocent person in jail, or is it worse to let a guilty person go free? They can both be pretty bad. We don't want any innocent people in jail being punished for no reason, but letting a guilty person go free, they could commit more crimes. And especially if it's a serious crime, if they've murdered somebody, we don't want them going out and murdering somebody else, and somebody else died that didn't have to. So sometimes it's a play on which one's the lesser of two evils. And depending how bad the type 1 error is, that's how you could affect this 5% value. If you don't want to make a type 1 error, if you think that one's worse than the type 2 error, then you make this 5% smaller, like go all the way down to 1% with it. Then you're less likely to make that error. Unfortunately, then you're more likely to make the type 2 error. So if you think the type 2 error is worse, you can't control that one directly. So what you do is you control the type 1 error and you increase it, make it as high as maybe 10%. Then you're more likely to commit that one, but then you're less likely to commit the other one. So that will change from problem to problem. Luckily, you don't have to decide what it is. They always give it to you in a problem. But because it can change from problem to problem, that's why this statement's not always true. In B, a confidence interval does not, if a confidence interval does not include a claimed value of a population parameter, then you can reject the null. It turns out with all these hypothesis tests in Chapter 8, you can get the same conclusion you get from them by doing a confidence interval from Chapter 7. And if your confidence interval has a range and the claimed value is not in that range, that's a way to decide to reject the null also. So B is true. Here's the one we usually do. If p-value is less than or equal to alpha, the decision is to reject the null. Otherwise, we fail to reject the null. That's saying you got to get an unusual probability. It needs to be less than or equal to alpha to reject the claim. Otherwise, we fail to. If the test statistic falls in a rejection region, the decision is to reject the null. There's two actual ways to do hypothesis test conclusions. The p-value is the more modern way, using computers and calculators. The old-fashioned way was using critical regions with tables in the back of the book, and you can still do that if you want. The textbook kind of shows both of them. They both lead you to the same conclusion. I usually just teach the p-value method because it's so much faster and easier to understand. But this is still true. D is still true. The answer here is A, because the 5% is not set in stone. It really ranges from 1 to 10%. Which of the following is not a true statement about error in hypothesis testing? A type 1 error is making the mistake of rejecting the null hypothesis when it's false. No, remember routine for fun? Routine, reject a true null, not rejecting a false null. A type 2 error is making the mistake of failing to reject the null when it's false. There's for fun. Routine for fun, failing to reject a false null. That is exactly what a type 2 is. The symbol alpha represents the probability of a type 1 error. That is true. Alpha, that level of significance they give you in every problem, that's the probability of a type 1 error. And that's the one we have control over by setting alpha somewhere between 1 and 10%. If we make alpha smaller, then the type 2 error gets larger. If we make alpha bigger, then the type 2 error gets smaller. So that alpha is the level of significance, but it's also the probability of a type 1 error. And here's the routine part from routine for fun. A type 1 error is making the mistake of rejecting the null when it's true. Yes, rejecting a true null. That's routine for fun. So routine for fun is what D and B are talking about. And then knowing that alpha is not only the significance level, but it's also the probability of a type 1 error. Then the answer is A. Okay, there's different types of tests you can run. And in your calculator, if you press, let's see if I can try to get this where you can see it, or maybe not so well. In your calculator, here we go. This, I don't know how well this is going to work with me holding it. Let's try this. Okay, so if you press the stat button, stat, and then right arrow twice, once, twice to tests, these first 6 tests are really what chapter 8 and 9 are about. The z-test and t-test, they're both for means, and when there's only one sample. Those are in chapter 8. Chapter 9 covers the 2-sample z and the 2-sample t, which are very much like the first 2, except there's 2 samples going on at once. So maybe there's a claim that men and women have different test scores. So there'll be 2 different samples, one for men, one for women, then you're doing one of the 2-sample problems. If you just have one population and you want to know, are those, is there an average that's true or not in something, there's just one population, then you do a z or a t-test. But the first 4 are all for means. 5 and 6, the 1-prop z-test and the 2-prop z-test are for proportions. And that's what's happening in this problem. In a Harris poll, adults were asked if they were in favor of abolishing the penny. Among the responses, 1,211 answered no, 490 said yes, and 369 had no opinion. What is the sample proportion of yeses? And what notation is used to represent it? So this is a deal again where there is some true proportion of people that are in favor of this. And that's represented with P, the population proportion. But the problem is we'll never know that unless we talk to every single person in the world, or at least every single person in the US. Often the population parameters are impossible to know. So in statistics, we have to rely on sample statistics to estimate what these population values are close to. A sample proportion is symbolized with P hat. The little caret above the P is red, P hat. So this has to be A or D automatically because P, for choice B and C, that's for populations. And P hat's used to represent a sample proportion. The sample proportion is simply found by taking how many people say yes to your question and dividing by how many there are. 490 said yes, and there was a total number asked of whatever, 1211. 1211 said no. 490 said yes, and 369 had no opinion. So if you add all 3 of those, the total is 2,070. Total people asked. So P hat is how many said yes over how many total were asked. 490 divided by 2070 in a calculator comes out to 0.2367. And that's choice D, 0.237. So, and this is the basis for these hypothesis tests. Somebody's going to make a claim that maybe the percentage is 25% for the whole population. Well, in a sample, we only got 23.7%. So is that enough of a difference to say that the claim is wrong or not? That's what all these hypothesis tests are about. Now, this problem didn't deal with that, but that's what happens in the whole process. Okay, so now we're going to go through the whole process. Here's another problem. A recent poll of 740 randomly selected adults, 587 said it's morally wrong not to report all income tax and tax returns. And usually what's funny is people want to punish everybody else for not doing this, but then they want to themselves cut and take all their any kind of loophole they can get that benefits themselves. They don't want to pay what they owe, but they want everybody else to pay what they owe. See here it says use a 0.01 significance level. So there's your alpha, or your probability of a type 1 error. This is what we're going to compare the p-value to. We need to get less than this in order to reject the null. To test the claim that 70% of adults say that it is morally wrong not to report all your income. So since the claim is that 70% say this, and for sure in our textbook, the null has to be p equals 0.7 no matter what. There's no other option. So we can eliminate A, D, and F right away because they don't have p equals 0.7. But the three that do have that have the three possible alternatives. P could be less than 0.7 in the alternative, P could be greater than 0.7, or it could be not equal to. The only way it's going to be greater than or less than is if the claim either said that directly, and then I would be putting it in the null, or if the claim had like an at least or an at most that technically would include an equal to. This one doesn't have that, it just says that it is 70%. So the opposite of that would be not 70%, and it would be E for the null and alternative. The null would be P is 0.7, and the alternative would be P is not 0.7. So now we're going to get the test statistic, which is a z-score here. All proportions are z-scores. We're going to get the test statistic and p-value by plugging in the 740 sample size, the 587 yeses, and the 0.7 claimed proportion of the population. So in your calculator, press stat and right arrow twice over to tests, and we're going to choose the fifth one because this is definitely about proportions, and it's the fifth one, not the sixth one, because there's only one sample here. They asked one sample of 740 people the question. We're not comparing two different populations like males and females. What do they think about income tax? So there's only three numbers to plug in. First it wants P0, that's trying to emphasize the 0 from the null hypothesis. So that would be 0.7. Then it wants X. X is the number of yeses, that's 587. And N is your sample size, 740, the three numbers in the problem. Then you tell it your appropriate alternative, which was the three choices we had. Either the P from the population is not equal to the claimed amount, or it's less than it, or it's greater than it. So I want to highlight the one that says not equal to. If it was one of those other two, I could move over there and select them. Calculate. And this will give me a t-score and a p-value, the very first two numbers that come up. Z is 5.535. The p-value, it looks like 3.11. Be careful. P stands for probability. Probability can't be bigger than 1. 3 is an impossible probability. Some people don't look at it close enough to notice that. It actually isn't 3. Look way at the end. It has an E -8 way at the end. Always look for that. That's the calculator's way of doing scientific notation. So literally you'd have to move the decimal 8 places to the left of that 3, and you'd get 0.00000003. There would be 7 zeros before you got to the 3. That's what that 3E -8 actually means. And the problem will end up wanting you to round it to 4 places. So to 4 places, it's literally 0. Almost looks like 0, even though it isn't. This is a highly unusual probability. It's so close to 0 that it's virtually 0. And z-scores typically don't go past 2 either. Remember, that was in chapter 2 or 3, that a z-score beyond 2 or -2 is considered unusual. So a z-score of 5.5, it says round to 2 decimal places, 5.54. That's an unusual z-score also. We usually don't get z-scores past 2. 5.54 is the value of the z-score. And the p-value rounded to 4 decimal places is 0.000000. 0, 0, 4 zeros, because it would take me 7 zeros before I finally saw any numbers. So technically it's not exactly 0, but it's so close to 0 that it's going to take 0 for an answer. So what this is saying is that if you take 740 people and 587 of them said yes to the question, you can actually see this in your calculator too, that right after the z and the p-value, right below that there's a p-hat. You don't need that for the answers, but you could look at that. P-hat is 0.79. 79% of our sample said yes to this question. The claim was that it was 70%. That's a pretty significant difference. That's what this is saying. That if truly 70% of people think this is morally wrong, the probability that you would see 79% say yes in a sample, there's a 0 probability of that happening. So, or virtually 0 percentage of that. So what that's telling me is this is highly unusual, since I always assume the null to be true unless I get something unusual going on. That's what's happening here. My probability and my z-scores, they're so unusual that it must be because I assume this to be true. The reason I'm getting unusual values, that assumption must be wrong. Assuming the null to be true must be wrong because I'm getting unusual calculations. Therefore, I can reject the null and say that the alternative is true. So because the p-value is less than alpha and 0 is less than 0.01, we reject the null hypothesis. And anytime you reject the null, there is enough evidence, there is sufficient evidence to reject the claim. And we're trying to reject the claim because the claim was in the null. So there's one problem. You're doing all the parts at once. You've got your null and alternative hypothesis. You're calculating a test statistic, you're calculating a p-value, and then you're doing a conclusion. That's a whole hypothesis test all in one problem, where the earlier problems were just doing some of the parts. Okay, so in chapter 8, they start you off with the one proportion z-test. Then they move to the problems involving means. And it turns out that if you're going to use the z distribution, that goes with the normal distribution. The z distribution is used anytime the population standard deviation is known. Other mean problems use the t distribution, and it's very similar to how it was in chapter 7 when you're doing confidence intervals. It all depends whether you know sigma or not. Sigma's population standard deviation. If you don't know that, if you have a sample standard deviation, then you have to use the t distribution. T distribution uses a concept called the degrees of freedom. It's always one less than the sample size. So if there's a simple random sample of 17, then I need df to be the number of degrees of freedom, and it would need to be 16. It does not denote the distribution of freedom, and it's one less than the sample size, so it's not C either. So that's needed to get critical values and possibly get your critical region if you're going to do it the old-fashioned way of the textbook. Okay, so now let's do a whole problem involving a mean. And notice it says the ages of actresses when they won an acting award is summarized by the statistics n equals 76, x bar is 35.5, and s is 11.2, but it's s, not sigma. We don't know the population standard deviation. All we have is s. So we can only do the t distribution or nothing. And in order to do either z or t, either they need to tell me the original population is normal. They don't say that here anywhere in the problem. And in most real-world situations, you wouldn't know that. Or the sample size must be greater than 30. And here it is. The sample size is 76. So yes, I can do a t distribution, just like in Chapter 7. And I will do t because s is 11.2. We only know s, we don't know sigma. Use a 5% level significance to test the claim that the mean age of actresses when they win an acting award is 32. So again, the claim is that it is 32. That's definitely in the null hypothesis. It's definitely not D. You would never put not equal to there. And then the opposite of that would be not equal to, so this would be B. And notice they got a mu here, not a P for a proportion. Then we're going to get a test statistic, but this time it'll be a t-score. There's only one sample here. So when I go to the calculator for which test I'm going to do, stat, go over to tests. There's only one sample, and I'm doing the t-distribution, so it'd be number 2 t-test. Now you have a choice between data and stats. We're actually going to do data in a second, but this one is stats. Stats is when they list all the answers for you. So they told me that this is from the null hypothesis. The null hypothesis is 32. Here come the stats. S was 11.2. Oh, sorry, I hit that wrong. S is 11.2. X bar was 35.6. And here's where the debate comes about. The claim is that their age was 32, but in a sample I got 35.6. Could that happen randomly by chance? Possibly. Or is that a significant difference where maybe the probability of seeing that is so small that I must have, the claim must be wrong, is why I'm seeing this result. That's what we're going to check here. N is 76. Again, the alternative hypothesis is not equal to, and then we'll calculate. So here's my test statistic. T is 2.80. No, this time they want 3 places. 2.802. And the p-value is 0.065. So the test statistic is slightly unusual because it's a little bit past 2. Although just barely past 2, 2.802. We're almost out to 3. Although t's can go a little bit longer. Round to 3 decimal places. Let me double check I typed that right. Oh, I do have a typo. Go back to tests, t-test. The sample mean wasn't 35.6, it was 35.5. Calculate. So the test statistic is actually 2.724. 2.724. And then the p-value is now 0.080, which again is a very small one. 0.080. Is that less than 5%? Yes. So since the p-value is less than 0.05, we reject the null hypothesis. And there is sufficient evidence, so right away I know the answer is C. The claim was that the age is 32, so that's the null. We're trying to reject it whenever it's in the null. There is sufficient evidence to reject the claim. So in other words, 35.5 is significantly far enough away from 32 to be able to say that there must be something wrong with that 32 claimed number, because we're getting such an unusual probability. Although it's not a guarantee that it's wrong, we're rejecting the null hypothesis. Maybe the null is actually true. We might be making a type 1 error where the null is actually true and we might be punishing an innocent person. We'll never know, but the evidence is in our favor. The probability that there is something going on was 0.008, but there is that small chance it could happen. That's 8 in 1,000. There's an 8 in 1,000 chance that we're wrong, actually. We might be making a type 1 error. We got a 5% chance of making a type 1 error whenever we set alpha at 0.05 also. Okay, last problem is one where we have 2 samples going on at once. So assume the 2 samples are independent, simple random samples selected from normally distributed populations. So we do know the populations are normal here. Do not assume the population standard deviations are equal. Now, as is usually the case, you usually don't know sigma. They would have to come right out and tell you sigmas for you to know that. We don't know sigma here, so we cannot do z-test. We can't use any kind of z-test here. And since there's 2 populations going on at once, There's the ones for home voltage and then generator voltage. And they took a sample of 40 of each one. So we have two different populations, each sampled with 40. So in the calculator, I've already typed all this in because this problem takes a while, unfortunately. But you go to Stat, Tests, and we had to choose between 2 sample Z and 2 sample T because there's 2 samples and it's about a mean. It's not 2 proportion because we're not dealing with proportions right now. And this is 2 sample T because all we have are statistics. We don't have sigma given to us. And here's a case where we want to click data instead of stats because of all this data that they're actually giving you. This is raw data right here. I don't know what X bar is. I don't know what S is. So what you have to do ahead of time actually for this problem, before you run this test, press stat, and before going over to tests, stay right here on edit and press enter. And we've used this for other chapters. I've already typed in all these because it takes about 5 minutes to do this. You have to unfortunately type all 40 of these numbers into list 1 and list 2. So get them all typed in there. And you have to go down the columns. The home voltage, you have to go straight down all the way to 20 of those and then wrap around here to 21. And do that all the way down to 40. That's L1. L1 is the first and third columns of numbers. Then the second and fourth ones are going in L2. So they'll end up being 40 numbers in L1, 40 numbers in L2. Then once you have them all in your calculator, now you can run the test. Press Stat, go over to Tests, and this is the 2 sample T-test. T because we don't know sigma. And if you click on data instead of stats, it just asks for which list are your data in. I have the first ones in list 1 and the second ones in list 2. Oops. And then the frequencies, I don't even know what that does, so just leave 1s for them. And then we got to go back to what our null and alternative it was. But it was, for a third time, mu1 is not equal to mu2. There was no indication of direction on them. It just said test the claim that the sample of home voltages and the sample of generator voltages are from populations with the same mean. So the claim is that they're the same. The alternative then would be that they're different, not equal to each other. The 2 sample t-test has an extra question in it. It wants to know, are you going to pool? Pooled yes or no? And actually says no or yes. And when in doubt, click no, and that's why no is first. Usually yes-no questions have yes first. The only way you can say yes to that is right here in the problem. The last sentence of the top line says, do not assume that the population standard deviations are equal. They have to say, assume that they are equal for you to click yes to pooled. If they say do not assume, then you definitely click no. If the problem does not have that sentence in it at all, then you still click no. So you always click no unless they say you can assume that. So I'm going to leave this on no to pooled. Calculate. So we'll get a t-test statistic. Now look how unusual that one is. Negative 15.9. So the p-value is going to be a very weird scientific notation again, because we usually don't go past negative 3, and here we got negative 15. Unless I have some kind of typo, we'll find out in a second. So let's see if my calculation is correct. Round to 3 decimal places. Negative 15.904. Yep, okay, it's good. But that's so unusual that the p-value is literally 0. Round to 4 decimal places. Because it was 6.3 e negative 26. That's really times 10 to the negative 26. There would literally be 25 zeros before you started seeing your numbers. So that's virtually 0. Watch out for those scientific notation ones. And since that's definitely less than any alpha, here the alpha is 1%, 0.01. But 0 is definitely less than 0.01, so we reject the null. There is sufficient evidence to reject the claim, because the claim was that they were equal, so that's definitely going in the null hypothesis. So there's one last thing here. It says the difference blank statistically significant. If you reject the claim, the difference is statistically significant. So one of these two methods is definitely different than the other, and it could make a difference in whatever you're trying to do. And it's not really up to us to decide which one's the better one, but we just want to show that there is some kind of difference. If there is a statistically significant difference, does that difference have practical significance? Now that's another issue. And the point is, go back and look at all the numbers. The numbers are all like 123, 123, 123, 124s, 125s. The numbers don't seem that far away from each other. So they can be statistically significant in that if the standard deviation is so small, these can seem far away from each other relatively. But in practicality, is 123 really any different than 125? It's such a small amount of a difference that it can have a statistically significant difference, but it might not have a practical difference. The sample means, and you can look at the sample means too, one of them is 123.4, the other is 124.5. They're so close together, suggests that the difference does not have practical significance. The generator could be used as a substitute when needed, because it's not that big of a deal. It's only a difference of 1. When you're already in the hundreds, that's not that big a deal. It'd be like going to buy a television, and one store has it for $1,005, and another store has it for $1,004. When you're already in very large numbers, a difference of $1 isn't a big deal, even if it turns out to be statistically significant. Okay, so there is practice exam 4 for chapters 8 and 9. All 16 questions are correct now. And in the homework tab, after you finish everything through chapter 11, there's now 5 practice exams here. 1 for each test you're taking. So there's not a test over chapter 10 and 11, but some of that is on the final exam. So I'll be making one last video next week that'll be a review of practice exam 5 for the final exam. So until then, enjoy and study practice exam 4.